So thank you very much for your kind presentation and giving me opportunity to present some of our results on magnetic microwires, which we tried to prepare for magnetic shape memory or magnetocaloric applications. And see, you can see the outline of my talk, which consists of some introduction on fabrication technique and the characterization of materials, including magnetoresistance, magnetocalorics, and structural characterization. I will try to be short because I see that we are a little bit short of time. So we're working in our laboratory with so-called glass-coated microwires. So these wires could be produced by rapid quenching technique, and so that these microwires consist of metallic nucleus and glass coating, and we can produce such materials in quite long, and the dimensions are micrometric. So it could be some of the achievements for use of this material for the different applications related with magnetic shape memory. And generally we can produce materials with diameters from about 1 to 50 micrometers, and it could be amorphous, nanocrystalline, granular, and recently we tried also to produce Husserl alloys or even different alloys with magnetocaloric properties. And you can see different functionality of that materials. They can have quite different functional properties like JMR effect, or even especially amorphous materials are now already applied for different sensor applications. And so here is just, in fact, I will present this afternoon a semi-plenary talk on amorphous microwires, and they can present quite useful properties like quite high giant magnetic impedance effect, which is useful for sensor application, or even propagation of single domain wall up to velocities up to 2.5 km per second, or even higher, for suitable for spintronic applications. And such materials, I already told that they already used for different applications, for sensitive, for sensorics, for example, smartwatch or cell telephones. And the important that these materials can provide almost the same dimensionality like thin films. This is the comparison of scale of microwires and the different materials prepared using rapid quenching technique. For example, wires, ribbons, conventional, and thin films prepared by sputtering. So our materials are low-dimensional materials. And the interest in Husserl type microwires is because they can probably, if they are prepared in right composition and right conditions, can prepare magnetocaloric effect and probably a magnetic field induced strain. And there are there are previous few works, attempts to do it, and I don't know what happened. And somehow motivation of our job is this paper published in Advanced Materials, that low-dimensional magnetic materials could be useful for applications, for example, for magnetic refrigerators. So the question is that the refrigerating capacity depends on different factors. For example, one is the volume of magnetocaloric effect, but another important issue is that these materials could have a higher surface to volume ratio, and this could enhance heat exchange rate between material and the surrounding liquid. And one of the possibilities to use microwires, because thin films is quite tricky to prepare of these materials. This, in fact, the transparency is on the same, that we are trying to realize to prepare microwires and to look for composition when we can get magnetocaloric effect and related properties suitable for applications. So additional motivation that I already mentioned, that our materials are about 1 order thinner than hair, human hair, and we can prepare from 1 gram of materials about 1 kilometer of microwires. So in this way we are saving the raw materials, and could have good mechanical and mechanical properties and corrosion properties because of insulating glass, which allow us to sometimes to enhance the mechanical properties of that materials. So we used a different experimental technique, so part of the fabrication facilities in our laboratory. So we measured magnetic properties using PPMS. Magnetic caloric effect we tried to evaluate from the hysteresis loops, and also we used some collaborators' facilities in Russia. They measured directly change of temperature, and we used also X-ray diffraction, and also for chemical analysis we use EDX spectra. One of the examples shown here for one of the microwires which we prepared during this work. And the magnetoresistance we measured by conventional way, shown here. So we evaluated the magnetoresistance from this relationship. So in fact, I just prepared several recent results. So usually as prepared sample present features like they even cannot show saturation even at low temperatures, which is somehow unusual. But one of the results which I present here, we found some kind of small hysteresis on magnetization curves, heating and cooling. And then we tried to measure electrical resistance versus temperature, and we found this typical hysteresis, a typical anomaly at temperature about 100 degrees, which could be signature of the magnetic transition. However, it's a little bit strange because we didn't observe such evidence of such transition, only a slight hysteresis on magnetization curve. And the magnetization is responsible for the magnetization curves responsible for the magnetic states, and however the resistivity is more responsible for the structural changes of our materials. And one of the important features that once we anneal our samples, we can release the internal stresses related to the fabrication technique. And we did it, and now our materials present saturation even for higher temperature. We present hysteresis loop with quite good typical ferromagnetic behavior, and Curie temperature near room temperature shown here. So in fact, we were trying to vary the engineering conditions and to find the right conditions to achieve the first order transition of this kind of material. So this is nickel manganese gallium typical microwires. And finally, we found the conditions in which we have observed this hysteretic behavior, Curie temperature near room temperature, and this means that we achieved somehow conditions, it was quite recently, which we realized possibility to observe magnetocaloric effects, and also this change of magnetic properties which are typical for first order transition of this kind of materials. So in fact, there are two more annealing conditions which we observed similar features. And then these materials we measure magnetic resistance, and these materials present magnetic resistance up to 2%. And of course, at room temperature, the magnetic resistance was not observed because in this state materials are already in paramagnetic state. And what was also interesting that after annealing, magnetic resistance was increasing up to 3–4% near room temperature, because probably coexistence of two different magnetic phases at this in these materials near room temperature. So we tried to evaluate magnetocaloric effect, and using conventional method. The magnetocaloric effect was not big, but still we observed some magnetocaloric effect in this material. And we also performed some structural studies. So as you can see through this picture, as prepared sample present with quite broad X-ray peak, which could be attributed to coexistence of BCC phase and amorphous phase. And then after annealing, you can see clear change of the structure. And finally, after annealing at conditions where we have hysteretic behavior, we found FCC phase about 75%, but still all the materials present nanometric grains. So these materials present crystalline structure, even after annealing. And just to mention that in similar materials we measured magnetocaloric effect, like change of temperature, but in the setup of our collaborators in Russia, and we also observed this magnetocaloric effect in different kind of nickel manganese gallium microwires. And for example, we also tried to remove the glass, and we found glass the effect was larger somehow. One more interesting feature that the Curie temperature of materials is affected by the annealing, by post-processing conditions. So, for example, all as prepared samples present quite low Curie temperature and irregular temperature dependence of magnetization. But if you anneal the samples, you can achieve Curie temperature near room temperature, and magnetization curves depend very much on the annealing conditions. And just to show the possibility, we mixed different sample annealed in different temperature, and we achieved broadening of the phase transition. This is second order phase transition near room temperature, which could be one of the possibility to use this property of the materials. And also another marker of feature that after annealing, all these materials present saturation. Without annealing, it was not. And this effect of glass removal, also on magnetization curve, the effect was remarkable, but not very big. How long time I have?
About 3-4 minutes.
Okay, so. Next, I will try to go faster next part of my presentation. This is so the problem was that during this preparation technique, manganese was always evaporating. Therefore, we tried with different compositions. For example, in nominal composition, we added manganese. In this case, the microwires had diameter 6 micrometers. And again, we found this dependence on annealing conditions, magnetization curves, and change of the structure on the annealing. However, we didn't observe these features like in the case of previous thicker microwires. And the problem should be related with the internal stresses, which are related with the fabrication technique. And the essence of this is internal stresses. The origin is coming from simultaneous cooling of glass and metal, and the glass have much higher thermal expansion coefficients, and therefore axial stresses about almost half gigapascal could be observed in most part of these materials. And in this way, we always study the materials with strong internal stresses, with initially axial direction, and we can even tune the strain volume of these internal stresses by changing the thickness of glass coating, as shown in this picture. So this is important point, and we tried with different compositions. For example, nickel, manganese, indium with cobalt additions, and the features were almost the same. So after annealing, we observed nearly room Curie temperature in all the materials. However, we didn't observe first order phase transition near room temperature. Recently, we tried with cobalt-rich materials. They have high Curie temperature above the possibility of our PPMS device, so more than 300 Celsius degrees. And at room temperature, they present squared hysteresis loop with coercitivity about 50 Ørsted, which could be suitable for different applications, for example, observation of domain wall dynamics And this is maybe the last slide. So just this week we prepared this new composition, not Hochschild alloy, but it could be also suitable for applications. So the advantages of this possibility, we can prepare long microwires with enhanced, so first of all your ratio, considerable magnetoresistance effect and magnetocaloric effect, and disadvantages we need to somehow to fight with the strong internal stresses and manganese evaporation. And I'm going to conclude, so this technique is probably suitable, interesting for this kind of applications, and provide some new possibilities. Last but not least, so in fact, well, I want to thank you, but so this is our group, one of the last seminar. Now Albert Fert, the Nobel Prize of Physics, formed part of our group because as a distinguished researcher of our university. And this is just announcement of the publication possibility in special issues of processing and all sensors. Thank you for your attention.
Okay, just very short. One of the interests of these micro wires is for magnetocaloric applications, as far as I understood. In which particular kind of applications you think these micro wires would be very best suited compared to other kind of materials?
I think, well, in fact, it could be interesting for micro actuators probably, or for a magnetic refrigerator. And in one of our first papers, we showed that glass, in fact, does not absorb the heat, but just the heat exchange is becoming slow. And therefore, if we can achieve the high magnetocaloric effect, it could be suitable. For example, you could put your material in liquid, and because of good corrosion, anti-corrosion properties, it could be suitable for that kind of application, for example. This is my opinion.